5.5 days. That is the number scientists published in late 2025 if every satellite in orbit lost the ability to steer right now, due to a solar storm, a cyber attack, anything. The calculated time before the first catastrophic collision is 5.5 days. That's not very long. In 2018, the same calculation gave you 164 days. We have lost about 158 of them, and that number is still falling. I want you to hold on to that thought for a moment, because none of this feels real if you're just hearing those numbers out loud. It would make much more sense to feel it in a real-life scenario. So, I want you to sit back and imagine it's an ordinary Tuesday morning. You wake up and pick up your phone, but to your surprise, there's no signal. You turn it off and then back on. Still nothing. You turn the Wi-Fi off and then back on once more, and still nothing seems to load. You decide to go over to your TV and turn on the news. It cuts in and out, and then finally it goes dark completely. You get in your car. The GPS won't connect. You know your local roads, so you don't panic. But the cargo ship navigating the port of Rotterdam doesn't have that luxury. Neither does the flight descending into LAX over the Pacific, where there is no ground radar. Only satellite positioning keeping 300 people separated from the aircraft ahead of them. At a hospital near your house, a surgeon pauses mid-surgery. The imaging system has gone offline. The backup needs an authentication ping from a server that no longer responds. The banking network freezes next. Not the apps, the infrastructure underneath them. Most people don't know that GPS satellites don't just tell you where they are. They broadcast timing signals accurately to 20 nanoseconds. That synchronize every financial transaction on Earth. When those signals stop, the global economy doesn't slow down. It locks up and freezes completely. By afternoon, the power grids on 3 continents begin desynchronizing, not from cyber attacks and not from the storm, from a single collision, 550 kilometers above your head that triggered a chain reaction nobody could see or stop. Because by the time anyone understood what was happening, it was already irreversible. We cannot simply go up and fix it. The debris field is too dense, it's too fast, and no rocket can safely reach orbit, not this month, not this year, not even this decade, and possibly not even in your lifetime. This is called the Kessler effect. The conditions for it are not approaching, they are already here. Now, let me explain some things to you. Low Earth orbit sits roughly between 200 and 2,000 kilometers above the surface. Everything in it moves at around 28,000 kilometers per hour, fast enough to circle the entire planet in just 90 minutes. At that speed, a marble-sized fragment hits with the energy of a hand grenade. A softball hits like a safe dropped from 10 stories. Size is almost irrelevant. Velocity is everything. So when I tell you that the European Space Agency's 2025 Space Environmental Report counted 40,000 tracked objects larger than 10 centimeters, 1.2 million objects between 1 and 10 centimeters, and 140 million fragments too small to track, I need you to understand that every single one of those is an active projectile, moving at 28,000 kilometers an hour with no pilot, no brakes, and we have no ability to stop it. Of the 40,000 tracked objects, roughly 11,000 are active satellites. The rest are dead spacecraft, spent rocket stages, and the debris from past collisions and explosions. SpaceX's Starlink constellation currently accounts for nearly 9,000 active satellites alone, with regulatory approval for up to 42,000. Here is why that number matters the most. The more objects you place into a fixed orbital band, the more opportunity for collisions you create. This isn't speculation, it's geometry. And the growth of megaconstellations has changed the geometry dramatically. The International Space Station performed debris avoidance maneuvers twice in a 6-day window in November of 2024. and again in April of 2025. In early 2025, a dead Soviet rocket body and a defunct communication satellite passed within 20 meters of each other over Kenya. 20 meters at orbital velocity. They missed, but the frequency of these near misses is accelerating as time goes on. The ESA estimates satellites now perform over 1,000 collision avoidance maneuvers every single year. Each one cost fuel that is finite. When a satellite runs out of fuel, it becomes debris permanently. Donald Kessler was a NASA scientist who in 1978 described a scenario most of his colleagues considered theoretical: a density threshold in orbit beyond which collisions become self-sustaining. Each impact generates debris. That debris hits other objects. Those impacts generate more debris. The cascade feeds itself, and critically, it does not need humans to keep launching anything to get worse. We now have evidence to know he was right. The 2009 collision. On February 10th, 2009, the active Iridium-33 communication satellite and the defunct Russian Cosmo 2251, a dead spacecraft that had been drifting uncontrolled for 13 years, collided over Serbia at a combined closing speed of roughly 42,000 kilometers per hour. The impact generated 2,300 trackable debris fragments. Both objects were obliterated instantly. The debris cloud is still in orbit today. It's still spreading, still tracked by NASA's Orbital Debris Program Office. That was one collision between objects we could see. It took years for the debris field to begin to thin. The smaller, untracked fragments, thousands of them, we simply cannot account for. Even the 2007 test. 2 years before the Iridium collision, China conducted an anti-satellite missile test, deliberately destroying its own Fengyu 1C weather satellite at an altitude of 865 kilometers, high enough that the debris will remain in orbit for decades before the atmospheric drag pulls it back down to Earth. That single test created the largest debris field in orbital history. Over 3,500 trackable fragments, thousands more too small to track. Multiple operational satellites have had to maneuver around the remnants. The ISS has had close calls with Fengyu debris. China's test and subsequent ASAT test by Russia, the US, and India demonstrated something that Kessler had warned about previously. Humans don't need accidents to poison the orbital environment. We do it deliberately and under current international law. Nothing prevents this. This is the tipping point. Here is the mechanism that makes Kessler Syndrome genuinely irreversible rather than just very bad. In orbital bands above roughly 800 kilometers, debris does not naturally decay for decades and sometimes even centuries. Atmospheric drag at that altitude is too weak to pull objects down on a meaningful timescale. So every collision at that altitude is mostly permanent. The fragment count in that band can only go up. Once debris density crosses a critical threshold, the math locks it in. Even if every country on Earth stopped launching tomorrow, the existing debris population would generate collisions. These collisions would generate more debris. The cascade would continue entirely without human input, feeding itself across years and then decades. Models suggest certain orbital shells may already be past that threshold. Not in the runaway sense, not yet, but the trajectory is clear. We are adding objects faster than the environment can absorb them, and the margin is narrowing every single year. The scenario I described in the opening wasn't a speculation, it was a consequence map. Let me take you through what actually fails and why. The GPS timing problem. GPS is not primarily a navigation system. Navigation is a side effect. The core function of GPS satellites is broadcasting an atomic clock signal accurate to 20 nanoseconds, and that signal runs underneath almost every network system on Earth. Financial exchanges use it to timestamp transactions and prevent duplicate processing. Power grids use it to synchronize phase across hundreds of miles of transmission lines. Mobile networks use it to coordinate thousands of simultaneous calls. The internet packet routing protocols depend on it. The U.S. Department of Homeland Security has assessed GPS as critical national infrastructure. A sustained outage doesn't just ground planes and confuse drivers. It freezes the global financial system, destabilizes power grids, and degrades communications simultaneously. Now, the weather forecasting. The 5-day hurricane track forecasts that give coastal cities time to evacuate exists because of those satellites. Without real-time satellite data, forecast accuracy falls to roughly 24 hours, and even that becomes unreliable past a few hundred kilometers from land-based radar. Hurricane Katrina in 2005 triggered evacuations 5 days before the landfall, moving over 1 million people based on satellite track projections. That lead doesn't exist without the satellites. The humanitarian cost of losing weather forecasting is not abstract. It is measured in the warning that won't be issued and the storms that will make landfall unannounced. Aviation over the ocean. There is no radar over the open ocean. Transoceanic flights, the routes that cross the Atlantic, the Pacific, the polar corridors, entirely depend on satellite communication for positioning and separation. Without it, oceanic capacity reverts to 1960s procedures, massive spacing requirements, slower speeds, and a fraction of current flight volume. The global air transport network effectively collapses to regional operations. The military dimension. Every major military has integrated satellites into its command infrastructure. Precise guidance, surveillance, early warnings, secure communications in active theaters, all of it runs through orbit. Lose it suddenly and the fog of war doesn't thicken, it becomes totally black. The risk that follows is not a technical one, it's a human one. Nuclear-armed states operating without satellite intelligence, without reliable communications, under sudden time pressure. That is the environment miscalculation becomes most likely. Kessler Syndrome doesn't have to directly cause a nuclear exchange to put one into motion. The lockout. Everything above assumes a partial failure. Some satellites lost. Systems degrade. A full cascade changes the equation entirely. If the most congested orbital shells become impassable, we cannot launch replacements. We can't repair what's already there. The infrastructure cannot be rebuilt because we cannot reach it. Current models suggest that a full cascade in the critical LEO bands would leave orbital space unusable for between 50 and 200 years. Not a temporary blackout, a generational lockout. Every technology that depends on orbit gone on a timeline that outlives everyone watching this video. Can we truly stop it? The frustrating answer is yes, technically, no, practically, not at current pace. Debris removal. The European Space Agency's Clear Space 1 mission, years in development, launching in 2026, will attempt to capture and deorbit one singular defunct satellite. This mission cost 86 million euros. There are approximately 29,000 dead objects larger than 10 centimeters currently in orbit. The price of removing even the highest risk fractions of those runs into the hundreds of billions of dollars. No country owns the liability for the objects they have put up there. No binding international law requires them to be removed. The economics of debris removal produce no revenue, only cost. So no commercial incentive exists to fund it at scale. The 25-year rule. The current international guideline asks operators to deorbit within 25 years of mission end. It is not law, and it is not actively enforced. It was written in 1990, when no one imagined that 42,000 satellite constellations, and even with full compliance, objects in higher orbits take decades to naturally decay, during which they remain active collision risk. SpaceX has pushed towards faster deorbit timelines for failed Starlink units, which is genuinely better than the standard. But with thousands launching per year, even improved compliance rates will leave a growing residue. The governance cap. Outer space is a legal commons. The foundational document governing it, the Outer Space Treaty of 1967, was written when the total satellite count was in the hundreds. It contains no meaningful mechanism for regulating debris, enforcing disposal, or restricting anti-satellite weapon testing. Updating it requires agreement between nations that are simultaneously competing in space for military, economic, and strategic dominance. The same countries launching the most satellites are the most resistant to rules that would constrain those launches. Progress is measured in working groups and voluntary guidelines, not binding obligations. The solutions that would actually work are not technically built. Mandatory deorbit within 5 years in high-density orbital shells, a binding international ban on debris-generating ASAT tests, a funded operational removal program targeting the highest-risk legacy objects. None of these require new technology. They require governments to treat orbital space as finite, irreplaceable resource in it, before the cascade makes the conversation irrelevant. Donald Kessler published his warning in 1978. He was not dismissed because people thought he was wrong. He was dismissed because the people felt distant, theoretical, manageable, something to solve later. Later arrived quietly. It didn't announce itself, it just showed up as a number, 5.5 days, down from 164 and still falling. The cascade hasn't started, so don't worry just yet. We still have a window, but the window is defined not by years or decades. It's defined by decisions, by whether the next mega constellations get launched with or without binding disposal requirements, by whether the next anti-satellite test is permitted to scatter thousands of fragments into band that ships and hospitals and financial networks depend on, by whether orbital space gets treated as commons worth protecting, or a resource worth exploiting until it's completely gone. Every civilization before ours has left marks on the planet. We are the first to start leaving marks on the sky. The question is whether we stop before the sky starts marking us back. As always, guys, stay happy and stay safe.